Hello, welcome back. So this screencast here is another example of calculating irreducible representation of materials for Phonon analysis. And in this case, I applied it to MoS2. So in another screencast, I explained the techniques and as well as the underlying theory for graphene. So if you do not know the theory, I suggest that you start by watching the other screencast at the link that's actually appearing on the top right corner right now of the screen. But if you're familiar with the theory, it takes about 15 minutes, by the way, to review it. But if you're familiar with this, let's just jump in MOS2. So this is MOS2 seen from the top or seen from the side view, and we are going to look at single layer in this screencast. So that structure has a molybdenum atom shown in purple here and a sulfur atom in yellow. I should tell you right at the outset that I explained this for MoS2, but it also applies for other transition metal dichalcogeny like WSE2, WS2, MoSE2, and so on and so forth. I mean, the symmetries are the same for the single layer, so there's no really no problem. You can reuse exactly everything I've done here for MoS2 for others. In fact, you will see that the fact we have molybdenum and sulfur has very little to do with the analysis of the symmetries. So first of all, we have to find the point group. So the point groups are the symmetry, correspond to the symmetry of the unit cell. And in the case of MoS2, the point group is D3H. So that's slightly different from D6H that we saw in graphene. And in fact, it's a little bit simpler. Even though the structure here is not flat exactly, it has a few atoms, it's a few atoms thick. It is simpler because the D3H character table, which is going to be again the main tools that we are going to refer to, the D3H character table corresponds to fewer symmetries as we found for the D6H for graphene. So I'm going to calculate the representation gamma n. So how the symmetries affect the atomic structure of the MoS2 for each of those symmetries, and I'm going to use one slide for each, and I'm going to try to explain that to you. And we are going to do exactly the same work as we did before. So by now you should be familiar with the character table. You can see there the characters for each of the symmetries and then the irreducible representations, which are noted A1 prime, A2 prime, E prime, A1 prime prime, A2 prime prime, E prime prime. The last three columns always come in handy because they explain how the function change. The functions like the linear, quadratic, and cubic functions change for the different representation. We are going to make use of the linear function as well as the quadratic function later in this presentation. So let's start with the first symmetry, and this is the E symmetry, always the simplest because it's the identity, it doesn't do anything. So in this case, of course, how many atoms in the unit cell do not change? Well, first of all, remember, how many atoms in the unit cell do we have for MoS2? We have only 3 atoms. So the number of atoms that don't change under the identity is 3. Now I have to tell you here on the bottom representation seen from the side, I colored the 2 sulfur in different colors. Of course, they are both sulfur, but I did this in different colors so that we understand that these atoms, even though they are in the same unit cell, they are both sulfur and so on, they are not equivalent from a structural standpoint. So the way to understand this equivalency, if you will, is the fact that you need both of those atoms, a blue and a yellow one in the unit cell, to reproduce the crystal. So if only you had one, that wouldn't be enough. Therefore, they're not equivalent from that perspective. In any case, the point here is that I showed the fact that they're not equivalent by using different colors on the side view. And so the character for the number of atoms that are not changing under the identity, so in other words, the character for gamma n is 3. That's easy. Now the threefold symmetry is shown here in the center of the hexagon. And again, the hexagon is not a true hexagon. The projection is an hexagon. That's how it looks. Well, we can look at the two atoms that we're interested in. Let's say three atoms, but the other one is under, of course. And see how they move. We have a threefold symmetry. That atom is going to be moved here. It's an equivalent atom. It's just in different unit cell, so that counts for 1. The yellow atom, which is actually orange on this screencast, is going to move here. And same thing for the bottom layer. And of course, that means that those atoms land after the application of the symmetry C3, they land on an equivalent atom of the lattice. Therefore, we have 3 atoms that do not change. They only change by a translation, since we have an infinite crystal, they're equivalent. So we have 3 as well. So that's the character. Now the C2 prime is a twofold axis that exists in the plane of molybdenum. And this one is actually a little bit more interesting. Let's look at molybdenum and also sulfur. So in this case, sulfur, I actually use it on the bottom layers. It's easier for me to do. Well, the application, of course, on molybdenum is that it doesn't change, since it's basically, I mean, we can pick that so that it doesn't change. It's on the axis that matters. Now, we can pick it on the axis that matters. Now, for the atom, for the sulfur atom, is actually upon the rotation C2 is going to be moved to a blue atom. Therefore, the two atoms are not equivalent, and it's of course true for the atom that was initially blue. And in that case, we have only one atom that's invariant. It's the molybdenum atom. That's why we put a 1 in the character table there. For sigma H, we actually have essentially the same effect. So the sigma H again is this plane which is in the plane of molybdenum atom. The molybdenum atom obviously do not change, but the sulfur atom just moved up. Same for the one on the top moves down. So only one atom is invariant, again, the molybdenum atom. So we put a 1 in the character table. Now, if we look at the S3 symmetry, S3 is a threefold symmetry followed by a mirror plane. So I showed the rotation axis in green with an arrowhead, and I showed the plane, I mean horizontal, going through the molybdenum. So if we start from these atoms, for example, we know that the molybdenum atom is going to move there, and then the reflection is nothing since the plane goes through the atom. And then for sulfur, the sulfur is going to be rotated here, but then because it's an improper rotation, is going to then be shifted on the other side. So it's going to do this for rotation and up for the mirror plane. In other words, the sulfur atom are moved to an unequivalent position under the S3 axis. So in other words, the yellow atom become blue and the blue become yellow, so they are not equivalent. But the molybdenum atom moves into an equivalent position actually itself. So we have a 1, only one atom does not change. Now the sigma V, which is another plane, it goes through those atoms, is actually a plane that's such that all 3 atoms do not move. So if we take these atoms, for example, clearly there's no effect. So we have a 3. Okay, now we go back to our character table, and I added one row, which is the one we just calculated together, the gamma n. And we remember that in order to get the gamma 3n, so the reducible representation of the displacement, so it's like if we put x, y, and z axis on each atom, so gamma 3n, is actually related to gamma n and a direct product with the displacement along x, y, and z. Now we've learned in the previous screencast that those displacements can be obtained directly from the character table, and I highlighted them in yellow for x and z. And again, x and y, x, y, and z, x and y, for x and y, sorry, they are degenerate since we have isotropy in plane for MoS2. Of course, we don't have the isotropy in perpendicular to the plane in Z. In other words, gamma x plus gamma y plus gamma z is going to be simply the sum of those two columns. Again, 2 plus 1, 3, minus 1 plus 1, 0, and so on and so forth. So you get those numbers. And now we remember, of course, the next equation. So we can now apply that equation there, where we get gamma 3n from the direct product of gamma n and gamma x plus gamma y plus gamma z. So we can obtain gamma 3n as the product of those two last rows that I put together. So 3 by 3, 9, 3 by 0, 0, 1 times minus 1, minus 1, 1 times 1, 1, 1 times minus 2, and 3 times 1, 3. And really, we are done. So just take 10 minutes and we are done for the reducible representation. And of course, since it's a reducible representation, we want to reduce it into irreducible representation. And as I explained in the previous screencast, the coefficients that we can obtain are obtained using that equation on the top. And once again, H is a total number of symmetry. So we have 6, 7, 8, 9, 10, so 5, 6, and 6, 12 symmetries. N is the number of symmetry per class. So for example, for the first class it's 1, the second class is 2, the third class is 3, and so on and so forth. And then we obtain this, we can apply this. It's a little bit lengthy calculation unless you do this in an Excel sheet. And once again, I invite you to do that. It takes like literally 1 minute to do. And what I reproduce on the bottom here, a calculation corresponding to that equation on the top, I did it on the bottom for each irreducible representation, A1 prime, A2 prime, E prime, and so on. And I find some coefficients. So these are the AIs. And I highlighted in yellow the AIs that are not 0. So you see that you can write that in a form that's more conventional. We have a direct sum. And by the way, I should have used this direct sum with a circle around plus on the previous slide as well, but that was implicit. But the gamma 3n, so the representation of the displacement, which are related to phonons, is actually pretty rich. We have A1 prime, 2E prime, 2A2 prime prime, and E prime prime. And on the last slide now, I can simplify and maybe analyze a little bit further by looking at the vibrations and the Raman activity. So the gamma 3n, I just show you what it is. But only some of those are vibrational mode because the others are pure translation. The good news is the pure translation, we already looked at them. These were the gamma x plus gamma y plus gamma z. I called them here gamma TR, so for translation. So they correspond to E prime and E2 prime, A2 prime prime. And therefore the gamma vibrations is whatever is left over from gamma 3n minus gamma translation, and we end up with those 4 possible acoustic mode, those 4 optical mode that we have in system like MoS2. And it's interesting that the total number of mode here is 6. But remember, E prime and E prime prime are doubly degenerate, so the real number of mode that we have is actually 9, which is normal because we have 3 atoms, 3 degrees of freedom, x, y, and z, so it's 9. So we are all good. You can see them in the character table, which is shown here, and I highlighted them in yellow, those that are vibrational mode. What's interesting here is that if you look at the quadratic function, 3 of those modes are Raman active. So Raman active mode are those that have a quadratic function, simply because it's how the polarizability changes during the Raman process. And I'm going to wrap this up by showing you the Phonon band structure. So this is the Phonon band structure. And we can assign all the different modes, and we can see those that are doubly degenerate, like the E modes, and those that are not. In blue, I highlighted the modes that are Raman active. And we can even have a representation with ball and sticks of these guys. First, the acoustic mode, so the translation mode here at the gamma point of the Brillouin zone. They are pure translation. You see A2 prime prime is a translation along Z, while E prime prime, one of the two E prime prime here, is actually a translation, an horizontal translation, but there is one equivalent in the plane of the screen. And finally, the other mode that we have, four other modes are shown by these ball and sticks, and these are the vibration in MoS2. So in 15 minutes, we can actually solve this problem, and we can keep applying this to many other systems. Thank you very much for your attention.